It is Thursday, and my name is Ann Merchant, and I work for the National Academy of Sciences, and that's you, Rick.
I'm Rick Lovard. I also work for the National Academy of Sciences.
And we're very glad that all of you are here today, and we're glad that we can welcome you here for our event with Kevin Hand, who is an old friend to the Academy and to the Exchange, and we're very happy that he could do this with us today. My job always is to start by explaining a little bit about what the National Academy of Sciences is and does, and partly what I can see on my screen is a picture of our building, because one of our friends from our AV department uses that as his hold screen. So I'm reminded of the building that I haven't seen for about 2.5 months now. But the National Academy of Sciences is a private, nonprofit institution that was created by Abraham Lincoln in 1863 to really help the nation steer a good course toward good policy using the assets from science, engineering, and medicine. We're also an honorific society. So to be a member, for example, of the National Academy of Sciences is the highest honor in American science. And we are joined by the National Academy of Engineering and the National Academy of Medicine. As you might imagine, the members of the Academy and all of our thousands of committee members have been very busy over the last couple of months with the COVID crisis, but they're also working on a variety of different topics in science and engineering and medicine. So the work of the academies has continued apace, but everybody is really happy to have lots of these virtual events to get us connected to lots of different science so that we're not always preoccupied with the pandemic. I've been doing something where I sort of take a little virtual tour of the things I've been doing. Rick laughs because I think I held up a canned good one week. Rick is ready to grab a canned good. Look, I can just see it coming. There we go. Okay.
I've got
all
canned
right.
goods too.
But I did want to mention, this is not a canned good, but it is food related. Steakums. Diana Williams, I thank you for this because Steakums wins the internet. You guys have to check out their Twitter feed. They are all over science. It is amazing. The person who runs their Twitter feed, huge shout out to this young man because it is incredible the amount of science they are putting out through their Twitter feed. Totally unexpected. Go check it out. Steakums. I don't really eat a lot of beef, but I give mad props to Steakum. The other thing that I did want to mention is that AAAS is going all virtual. For those of you who are connected to the science community, the American Association for the Advancement of Science has announced that their February meeting is going to be completely virtual. In February, it was the last AAAS was the last big in-person meeting that I attended in Seattle, and I think that's true for a lot of us in science. So they've already said that they're going all virtual for 2021, which should be interesting and fun and exciting for a lot of us to see how that unfolds. And then SpaceX. Yesterday was the big event that almost was. It's why we decided to go for a Thursday event instead of a Wednesday event. But I think that there's a do-over, so we get to see that, and I think we're all excited that will happen at some point. I think there are 2 alternate dates, so we know we can tune into that. And then in personal news, my chicken coop is almost done. So at one point, I'm going to show up here with a little tiny chicken and show you that. Not a canned good, but a little tiny chicken.
I can't do a chicken. I can't chicken.
But I know you want a chicken coop. So the other thing that we always want to explain is a little bit about the Science and Entertainment Exchange. And we know that some of you are new to our events, new to Academy events perhaps. Certainly sometimes we have people here that are new to Science and Entertainment Exchange events. And I think it's sometimes surprising that the Academy does anything with the entertainment industry. But for those of you who are from our entertainment audience and the people that come to Exchange events, you're thinking, no, this is exactly what the Exchange does. But it's Rick's job to explain that program because he directs it and to explain what the Academies is doing out in Hollywood, which is where Rick is.
Hi, I'm Rick Lovard. I'm the program director of the Science and Entertainment Exchange. First, I want to thank a couple people for helping us out, making this event possible. Moises from the AV team at the NAS, thank you. Courtney Sloan, Jeff Fishman, and Sachi Gerben from the Exchange and NAS. The Science and Entertainment Exchange is a film consulting service or media consulting service. If you are making a TV show, a video game, a movie, a piece of mass media, you have a question about science, you can email me or Sachi or call us at 844-NEED-SCI, and we will connect you with a scientist for free. We've done over 300 events like this and over 3,000 consults since we launched over 10 years ago. Some of our movies that we've worked on: Avengers Infinity War, Man of Steel, Black Panther, Captain Marvel. If you are a STEM professional and you are new to the Exchange's work, and maybe you heard of us through some other, through cultural programs of the National Academy of Sciences or some of our colleagues at NAS, please, we're always looking for volunteers. We're always interested in scientists who would like to get involved and do these types of consults. I also would be remiss if I did not thank our sponsors, Howard Hughes Medical Institute, without whom this event would not be happening today. So thank you very specifically. Your dollars made this event happen, so thank you. And Alfred P. Sloan Foundation, Walt Disney Company, Film Nation, Google, Lyda Hill Foundation, Corteva, and individual donors like many of you. Thank you for everybody who clicked the donation button. If you have given $100 or more in 2020, we are going to send you one of these. It's a little challenge coin. It's individually numbered, super cool. We're very excited about it. And for those who are coin holders, either from last year or this year, we're going to do some extra content for you. We're actually going to do a whole extra event. So if you're interested in getting those invitations, please give if you can. We know it's a crazy time. Not everybody can give. And so we will always have free events, mostly free events all the time. But we're going to do a little extra for those folks who are able to give a little. So thank you very much. So today's event structure, you are going to hear from an astrobiologist. Also, I'm very proud to say, planning committee member for the Science and Entertainment Exchange, Kevin Hand from NASA's Jet Propulsion Laboratory. He will be speaking for 20, 25 minutes, something like that. If at any point during his talk you have a question, look down here. It should say Q&A. You click the little Q&A thing, a little window pops up, you type in your question, and I'll be on the other side trying to curate and get as many as I can answered in the amount of time we have, which will be very limited. So I'm really sorry if for some reason didn't get to your question. We'll do the best we can. Also, I gotta say this, the Alien Oceans event is around Kevin wrote a book. I guess this is part of adulting, is that suddenly your friends start writing books. If you do, if you are interested, if you want to learn more after hearing Kevin's talk, please support your local bookseller and go run out and get a copy. Back to you, Anne.
Well, I'm just the handoff to really invite Kevin to join us now, because he's the main event. He's why all of you are here. And we were really glad, I think that we've had Kevin on our stage a few times now, and we're always glad that we do. And our audiences are always especially glad when we do, because Kevin gives an amazing talk. When Rick said it'll be 20, 25 minutes, I reminded Kevin before we started, do you remember that time I broke a glass when I was telling you your time was up? And I think the audience was like, oh, stop. We just want him to keep going. So I'm going to turn it over to Kevin to give him as much time as possible, because I've already seen some of his slides and I want to hear all the narrative that goes with it. So it's over to you, Kevin, and thank you again for being here.
Thanks, Anne. Thanks, Rick. Can you hear me okay?
Yes.
Thumbs up there? Perfect. Excellent. And thank you for the invite. It's a pleasure to be here. Obviously, we all wish that we could be doing this kind of stuff in person, but it has been an interesting experiment in science communication and getting the information out there. Yesterday was obviously an incredibly exciting day with a bit of an anticlimax due to the weather. An exciting day for human exploration, and hopefully Saturday or Sunday the weather will clear and we'll get back to human exploration. Today, my talk about alien oceans on Earth and beyond is a bit of a robotic intermission. We're going to be talking about robots used for space exploration and for the exploration of our ocean. And the driving topic is the search for life beyond Earth and gaining a better understanding for life that exists within the alien ocean depths of our own ocean. Now, this question of whether or not life exists beyond Earth is one of humanity's oldest and most profound of unanswered questions. And my title mentions aliens. And just to be clear and to set the appropriate level of expectations, I will not be talking about UFOs, alien abductions, ET, or plushy little creatures that you can get at your local toy store or could get at your local toy store. My work and much of the work of my colleagues and NASA and JPL focuses on the search for simple organisms, microbes, slime mold. It's such a discovery of even a single-celled organism would be truly revolutionary for the science of biology. Now, it's a question that has captivated my imagination since I was a young child. This is me. I grew up in the beautiful Green Mountain state of Vermont, and was inspired by books like this from National Geographic, Our Universe, and shown here are many of the bizarre alien creatures that are shown within that book. I'll give that just a second to come through on the Zoom there. Some sort of balloon creature in Jupiter, some sort of big-eared mouse on Mars, and even some sort of dinosaur on the icy surface of a moon of the outer solar system. And so this question has captivated me since I was a young child. I like to show this image for another reason, and that is that the Green Mountains there give you a sense for how much biology our home planet has. Our planet Earth, is covered with life. Just about everywhere you look, high, low, top, bottom, hot, cold, you find life. And the story of the search for life beyond Earth is in part the story of our beautiful blue planet reaching out into the cosmos. And here you can see the Earth, the blue little marble here, and coming out of the Earth are these lines, each of which represents a spacecraft, a robotic spacecraft that has gone off to the moon or Venus or Mars or the sun or Mercury. And there's just a few lines that go out beyond the asteroid belt to worlds like Jupiter, Saturn, Uranus, Neptune, and Pluto. And by merit of these few spacecraft with names like Pioneer, Voyager, Galileo, and Cassini, and New Horizons, by merit of these spacecraft, we now have enough data to make an incredibly bold prediction, which is that oceans of liquid water exist beyond Earth. It's shown here is a portrait of the ocean worlds of our solar system. And this may be just the beginning. There may be many other worlds that could also be added to the list. But shown here, of course, is the Earth at the center with the ocean that we know and love and need to protect and that we need to study more. But around the Earth, I've placed Europa, Ganymede, and Callisto, 3 moons of Jupiter, Titan and Enceladus, 2 moons of Saturn, and I've even placed Neptune's curious moon Triton. These are worlds that are covered in ice, but beneath their icy shells, and I should say Titan has an atmosphere, and beneath that atmosphere is its shell of ice. But beneath their icy shells, we have good reason to predict that vast, potentially global liquid water oceans exist. These are oceans that likely exist today, and in many cases, these oceans may have persisted for the history of our solar system. Now, these ocean worlds, these alien oceans beyond Earth, are really changing the way we think about habitability. In the early days of astronomy and planetary science, when we thought about what it took for a world to be habitable, that kind of habitable zone was metered by the distance from your parent star. In other words, you needed to be at just the right distance from your star, in our case, the sun, so as to have enough energy to maintain and sustain liquid water on the surface of your planet, in contact with a nice thick atmosphere. And it turned out that if you were like Venus, you were too close and you got too hot. If you were like Mars, you were too far away and you were too cold. But if you were at the Earth-Sun distance, then you had just the right amount of energy to maintain and sustain that liquid water ocean on the surface. Now, the story with Venus and Mars and the Earth is much more complicated than that, and certainly we think Mars was warmer in the past, and Venus might actually have been a bit cooler in the past and could have had a surface ocean. But suffice to say, this traditional habitable zone, this kind of Goldilocks scenario of too hot, too cold, just right, is an old Goldilocks. There's a new Goldilocks in town, and it's a Goldilocks for habitability, where the energy for maintaining liquid water, the energy for maintaining liquid water oceans, comes not from your parent star, but rather from the tidal tug and pull that many of the moons of the outer solar system experience as they orbit giant planets like Jupiter and Saturn. And there's no better example of the power that results from this tidal energy dissipation than the moons of Jupiter, and in particular, Jupiter's innermost large moon, Io. Io does not have an ocean, but it is the most volcanically active body in our solar system. And it is so volcanically active precisely because of the stretching and tugging and mechanical energy that goes into Io as it orbits Jupiter, which is some 318 times as massive as the Earth. And in that little inset, you can see the plume of a volcano near the North Pole of Io. There are volcanoes erupting on Io right now, and they are powered by that tidal tug and pull. And so within the Jovian system, the four large moons, the Galilean satellites, present a kind of new Goldilocks framework, where in this case, Io is kind of like Venus in that Io has got too much tidal energy. It's too energetic. It lost any water that it may have once had. And Callisto, though we think Callisto likely has an ocean, Callisto is not yet fully engaged in the tidal dissipation with Jupiter. And so it's got a whiff of radiogenic decay, of heat from the heavy elements, and not really much of any tidal energy to sustain an ocean. But in the center, we've got Europa and Ganymede. And Europa in particular, we think, may occupy this kind of new Goldilocks zone mediated by tidal energy dissipation, such that it has an ocean roughly 60 miles in depth, or 100 kilometers in depth. And that ocean has a rocky seafloor, and its ocean is overlain by a relatively thin ice shell, an ice shell of maybe a few to as much as 20 kilometers in thickness. An ice shell that's thin enough that we think that the ice serves as a window into the ocean below. In other words, the composition of the ice is likely telling us about the composition of the ocean. And so the fact that these alien oceans exist beyond Earth is incredibly compelling in the search for life beyond Earth, because if our study of life on Earth has taught us anything, it's that where you find the liquid water and where you mix that liquid water with elements and energy, you almost always find life, whether it's life in extreme environments, such as the Rift Valley, shown here in the top right, the dry valleys of Antarctica, shown at the bottom right, or hydrothermal vents in the deep ocean, whether it's life in extreme environments or life of extreme lifestyles. All life on Earth depends on liquid water. I like to show this for another reason, and that is that for all of the extremes of life on Earth, from the tiniest of hydrothermal microbe to the craziest of rock star, for all of that incredible and beautiful diversity, all life on Earth is connected by the same tree of life. And shown here is an incarnation of that tree of life that was created about 65 years ago. And this tree of life is sort of that canonical tree with branches that show trilobites and dinosaurs and early hominids. But this, of course, is the tree of life as we now know it. And this tree of life is dominated by microbes. The major branches up here and over here and even down here are all microbes. For reference, Mick and Keith are, and all of us and everything on that old tree of life is somewhere in there. And so all life on Earth is based on DNA, RNA, proteins, and even ATP. And we're all based on the liquid water solvent and carbon chemistry that underpins that DNA, RNA life. These alien oceans beyond Earth present the prospect of searching for life that is alive today, living in these oceans, and new trees of life, perhaps separate second or third or fourth independent origins of life in our own backyard, right there in kind of the near real estate of our solar system, places where we can actually go and send robotic vehicles to search for signs of life. And again, such a discovery, even if it was just the tiniest of microbes, would revolutionize our understanding of biology and whether or not biology works beyond planet Earth. So how do we think we know these oceans exist? Quick little sip of coffee. For the most part, much of that begins with the robotic spacecraft that NASA builds and flies. And shown here are the Cassini spacecraft on the left and the Galileo spacecraft on the upper right. And proper credit needs to, of course, be given to the ear on the ground, the Deep Space Network, which gets the signals that are transmitted back from the robotic spacecraft. And today, I'm just going to briefly go through Enceladus and Europa, and then we'll come back to our home planet and talk a little bit about some of the exploration that we're doing within Earth's ocean and how we've got a win-win of bridging that exploration on Earth to the future exploration of these alien oceans. So first, Enceladus. Enceladus is a beautiful moon of Saturn. We, of course, know Saturn by its rings. Here's Enceladus with the rings and Saturn in the background. Enceladus is a curious little moon. It's just about 500 kilometers in diameter. That's roughly 300 miles. That's about the distance from Chicago to Cleveland. If you zoom in on Enceladus, the way the Cassini spacecraft enabled us to do, you see that Enceladus's icy surface is telling a curious story. To the north, you see that Enceladus's ice is pockmarked by all of these craters. And to planetary scientists and astrobiologists, craters are an indication of an old surface. And just like footprints in the snow, where the more footprints, the older the snow is. But to the south, you see very few craters. That's a very young surface. And along with that, you see these fractures, what have come to be known as the tiger stripes, stretching across the south polar terrain of Enceladus. And when the Cassini science team first saw those, they then decided to send the spacecraft at just the right approach angle such that this beautiful picture could be taken, shown here. Where out of those fractures, you see these jets. These are jets of water that we think are coming from an ocean below. Now, if I were in a amphitheater right now and you were all a live crowd, hopefully I would hear the following, a nice ooh and ah. That's one of the sad things of having to do this over computer. But this is a image that should drop your jaw and make you ooh and ah with astonishment, because what you're seeing are jets of an alien ocean erupting out of Enceladus's ice shell. Here's what some of those fractures look like up close. If you could dive into some of these darker regions here and survive, you might actually make it down to the ocean below. Here's another image. And part of why I like this image is because you can see some of the area where the ice appears kind of soft. And this is perhaps fresh Enceladian snow that has come out of a plume erupting out of one of these darker regions here. So these jets are erupting out into space, and they contain not only water, but the mass spectrometers on the Cassini spacecraft have also revealed that there are salts in the plumes, there are organics in the plumes, there's even hydrogen in the plumes, a lot of compounds that indicate not only do these jets connect with a subsurface ocean within Enceladus, but the chemistry of the jets also gives us good reason to predict that that ocean has a rocky seafloor, and that rocky seafloor may actually have active hydrothermal venting, active hydrothermalism. And just for reference, this is what I mean when I talk about hydrothermalism. This is an image that I took at the bottom of the Atlantic Ocean, showing a hydrothermal vent that serves as a chemical oasis for life in the depths of our ocean, where it's too dark for photosynthesis to power life, but where the chemistry of the hydrothermal vents can power chemosynthesis, allowing microbes to use the chemistry to build an ecosystem, and then the organisms either eat those microbes or subsist symbiotically off of those microbes. So we think that on Enceladus, the picture might look like this. We've got those jets in the South Pole. We've got an ice shell that's a few tens of kilometers in thickness, perhaps a bit thinner, at least in certain regions. And we've got an ocean that's a few tens of kilometers in depth. And then we've got that rocky interior that might give rise to water-rock interaction that could be important for life and habitability. That's Enceladus. I want to quickly move to Europa. Europa is a much bigger moon than Enceladus. It's about 3,000 kilometers in diameter. That puts it on par with our own moon in terms of size. And here's Europa shown for comparison with our moon and the Earth, all in scale to Jupiter, which again is 318 times as massive as the Earth. And so again, it's that tidal dissipation that Europa experiences as it orbits Jupiter that gives rise to its subsurface ocean. Now on Europa, the Galileo spacecraft that flew by Europa did not directly see any jets of water, any plumes erupting the way the Cassini spacecraft did at Enceladus. And so the evidence for an ocean within Europa is a bit more subtle, but it's beautiful, beautiful physics. And shown here is a breakdown of how I like to describe that physics and what it took to discover that ocean. Today, I don't have time to go through that in detail, so I'll just make a plug for the book. There's a lot of detail in the book on the physics of this and a lot of great stories. I highlight a friend, a colleague, and a mentor of mine, Margie Keevelson in particular, who's did some of the most incredible work with a magnetometer and the induced magnetic field around Europa that really was the linchpin in revealing Europa's salty subsurface ocean. And so in this video, you see that picture for what we think Europa looks like. It's got that rocky seafloor, this deep, roughly 100-kilometer ocean, 60 miles in depth, and then this ice shell that is cycling with the ocean below. And that cycling of the ice leads to some bizarre geologic features. Here's Europa's surface up close as imaged by the Galileo spacecraft. Something with that tidal energy dissipation and movement with the ocean below causes this kind of fracturing and rafting of the ice. It's far too cold for these European icebergs to break off and float on their own. Europa's surface is at about 100 Kelvin, or roughly minus 280 degrees Fahrenheit. And yet you see these kind of puzzle pieces that were once connected together, and all of those fractures were caused, we think, by the tidal tug and pull. Here's another image showing a larger region. Again, all of those stripes and little icy blister-like features we think are caused by heating from the interior and flexing and cracking of the ice shell. A lot of tectonism and geologic activity that we don't yet fully understand or know how to explain. And that's part of what's exciting about getting back out there. I want to call your attention to the reddish, brownish, yellowish color that you see here. This has been a mystery for a long time. So I'll just dive in briefly into some recent results that are pretty exciting, at least in my nerdy opinion. And it brings us to our lab where my team works at JPL. It's the Ocean Worlds Lab shown here. Since I can't wake up in the morning and go to Europa, we have to build Europa in the lab. And we've got a couple of ultra high vacuum chambers that we endearingly refer to as our Europa in a can, or our Enceladus in a can, or our Titan in a can. Pick a moon, we can replicate it in the lab. And in one of our experiments that we did a number of years ago, we put some table salt, some sodium chloride, into our Europa in a can. Now, as you all appreciate, sodium chloride, table salt, is also the predominant salt in our ocean. And there's good reason to think it could be a predominant salt within Europa's ocean. Now, unfortunately, table salt, looks white. We all know that from dousing our food with it. And along with looking white, it's also spectroscopically white or flat. And that means you cannot detect it even with fancy spectrometers on board a spacecraft or incredibly powerful telescopes. But what we found is that when we put this salt into our Europa chamber, put it down at Europa temperatures and pressures, and then irradiated it with high energy electrons in a way that's similar to what happens to the surface of Europa, it changed color to the eye and also spectroscopically. We found a few little features in the spectra that differed from the flat white spectra of unirradiated salt. And you can see that sort of brownish yellow caramel color of the salt after we did the experiment. And so once we did that, my colleague Samantha Trumbo is a brilliant grad student at Caltech, working with my friend and colleague Mike Brown. Samantha got time on the Hubble Space Telescope, shown here, and was able to get Hubble to point at Europa and collect some spectra. And what you're seeing here in black over on the right, these sort of these black wiggly lines shown as a function of relative reflectance and wavelength, that's actual data from the Hubble Space Telescope of Europa. And then in red, that red line is from our lab, and that's a spectrum I took of the irradiated salt. And that little dip, and the fact that the black spectrum from Europa matches that little red dip from the lab, tells us that this discoloration on Europa's surface is almost certainly sodium chloride from an ocean below that's come up to the surface and been irradiated on Europa's surface by that charged particle irradiation from Jupiter. So that's some exciting results. And just briefly, I'll describe what's next. In the years to come, NASA has committed to launching the Europa Clipper mission, shown on the left. This is a mission that will orbit Jupiter and fly by Europa some 45 times. The European Space Agency has committed to their Jupiter Icy Moons Explorer, or JUICE mission, and it will fly by many of the moons of Jupiter and then go into orbit around Ganymede. Coupled with that, we're also working on a concept for landing on Europa, but NASA has no commitment to that mission yet. But we're crossing our fingers that in the decade to come, or decades to come, we might advance that exploration. NASA has committed, at least in the early stages, to a mission that would get out to Titan. And I haven't spent any time today talking about the remarkable world of Titan and its bizarre seas of methane. And this mission, PI'd by my friend Zibby Turtle at the Applied Physics Lab, will parachute a robotic spacecraft into Titan's atmosphere, and then it will helicopter down onto Titan's surface and then hop around investigating different regions. An absolutely stunning mission that'll hopefully land in the 2034, 2035 timeframe. Now, as amazing as all of those missions are, and part of what I love about those missions is that we are getting out and exploring these alien oceans, but there's a beautiful win-win of exploration, and that is that as we advance our capabilities to explore Europa and Enceladus and Titan, these other alien oceans, we are developing the technologies to get into those oceans, and we are testing them out here on Earth. We are advancing our capability to do more in-depth, literally more intensive, more long duration, and more scientifically advanced studies of the ocean of our home planet. And that's incredibly important to me and my colleagues, and it's incredibly important to Earth science, that we do a better job of studying and protecting our ocean. So I'm going to briefly share with you some of the robotic and technology developments that we're working on, and I'll finish about the latest science in the depths of our ocean. First up is the North Pole, or at least a region in the North Pole that is covered by ice and under which there are hydrothermal vents. As a little plug for an incredible piece of software, the little globe views that I'm showing you today are snapshots from eyes on the solar system or eyes on Earth. And that's some free software that JPL and NASA developed that allow you to play with all sorts of data sets. So I encourage you to download and play with that. Don't do it right now. I don't want you to crash your computer or stop listening, but it's great software. So here's what that Arctic Ocean looks like, covered in ice. This is the Polar Stern, and a beautiful research ship operated by the German Science Board. And I was privileged to have a berth on that in 2016. And I was part of a JPL Woods Hole team that was deploying a robotic vehicle that can operate in autonomous underwater vehicle mode, AUV mode, or in joystick robotic operated vehicle mode. And this vehicle is taking some of the software and hardware and some of the developments that are being advanced for space exploration and applying them in advancing robotics for exploring our own ocean. It's an incredible system that has the advantage of being able to kind of go off on its own while the ship above floats due to the drift imposed on it from the ice. Here it is going overboard on a big crane with the fiber optic that would pan out from that little system on the back end here. I don't have a lot of time to go into depth on this today, but I'll simply say that this vehicle is a pioneering vehicle in our ability to explore the polar regions where the ice cover actually makes it really, really hard to get into the depths of the ocean, because the ice impedes our ability to recover and deploy such vehicles. We didn't find hydrothermal vents as part of that expedition with the NUI vehicle, the Nearest Under Ice vehicle, but we did find a mountain covered with sponges, and those sponges were decorated with starfish and tiny tube worms and shrimp and other creatures. And here's just a quick picture of the next generation of that vehicle, which uses even more space technologies that are making it hopefully more capable and being able to be deployed with longer duration. Next quick stop is Antarctica, where climate change is ravaging the ice. And our team spent about a month down there this past November and December at the Casey station that's operated by the Australian Antarctic Program. We were delighted to be guests and partners with them. And they even put up a little Europa sign on their place marker here. And down there, we were testing out this robotic vehicle, our Buoyant Rover for under ice exploration, a two-wheeled vehicle that the penguins loved. They showed up almost like little OSHA inspectors coming to do an inspection. When deployed under the ice, this vehicle is buoyant, so it roves on the under the side of the ice and allows us to get an undisturbed view of the ice-water interface. And there's a lot of interesting chemistry and biology that occurs here. Here's a quick snapshot from the rover eye view. And you can see all of these algal mats and the fish eating on those algal mats. Part of what our team is interested in is what happens when the sun sets and the ice goes into darkness and photosynthesis can no longer power these microbial mats or feed the fish. What then happens to this ecosystem? Well, with this robotic vehicle, our goal is to have it operate under the ice for a full year and communicate via satellite link back to us at JPL, where we can collect the data and images to see that ecosystem up close. Nobody's ever really done that before, and we're hoping that our robotic system can enable that. So I'll finish with the exploration of this curious little red dot out in the Pacific. Though this might look like an inconspicuous red dot, and it might look like a random place in the Pacific Ocean, it's quite a bit more than that. It's the Mariana Trench. This is the deepest region in our own ocean. It's 11 kilometers deep, or about 7 miles. And it turns out that the pressures within the Mariana Trench are comparable to the pressures in the depths of Europa's ocean. So it's a very interesting analog for both technology and the science of what might be happening. In 2012, I was a science team member on the National Geographic, James Cameron, and Rolex expedition, where James Cameron piloted this submersible and was the first human to get back to the deeps of the Mariana Trench since 1960, when the massive Navy vehicle, the Trieste, made that dive. And though this vehicle was incredible, I want to focus on the robotic vehicles, the landers that were built by Kevin Hardy, Larry Herbst team, that allowed us to get a longer term picture of what's happening in that deep, dark abyss. Here you see the end of the robotic arm from that lander, and at the end you see a fish head in a net trap. And after many hours, these curious creatures came out of the darkness and started feeding on that fish head. These are shrimp-like creatures with a face that only a mother could love. These shrimp-like creatures were not just eking out a living in the depths of the Mariana Trench. They were thriving. They came out in the dozens, then the hundreds, then the thousands. And so in that deepest, darkest depths, we found life thriving despite all of these incredibly harsh environmental conditions. And so these organisms are quite extraordinary. Whenever I show this picture, somebody is always wondering, what did they taste like? Did anybody eat one? Sure enough, one of the engineers did in fact eat one of them after I was done dissecting it. To put it politely, after he ate it, he rapidly went to the side of the ship and returned the chewed up shrimp to the ocean from which it came. Yeah, it did not taste good. But on a subsequent drop of these landers, we were able to answer a key question, which is that those amphipods, those shrimp-like creatures, were eating the fish head. And that's all well and good, but we were curious, what's the base of the food chain? How is this ecosystem surviving without the sun? And in this video, once the debris clears, we saw this beautiful outcrop of rocks. Nobody had seen rocks and talus, boulders at this depth in our own ocean before. And when we zoomed in on these rocks, this is what we saw. And biologists here would ooh and awe at these little filaments coming off the rocks. These filaments, we think, are microbial mats that are surviving off of the chemistry of the water-rock interaction with the deep ocean. These microbial mats, we think, might be the food for those amphipods when there's no baited fish trap around. Up close, I looked at this material under a scanning electron microscope, and at the highest resolution, focusing deep in instead of far out. This is what some of those microbes, those putative microbes, from some of that mat we think looks like. Now, we didn't actually grab a sample, so I want to be cautious with this presentation. But if in fact the material we were able to serendipitously collect is representative of those mats, this may well be some of those microbes, the little spherical things that you see. So here we are in the deepest, darkest depths of our ocean, and we find that biology works. And that gives us some confidence that beyond Earth, in the depths of Europa's ocean, Enceladus's ocean, and Titan's ocean, biology might work. It might have given rise to a second independent origin of life. And it could be just swimming away in that distant ocean. So I'll conclude with my all-time favorite image. And it's a picture drawn by the hand of none other than Galileo. It's an image that shows Jupiter at the center, that pinwheel-like structure, and these 4 points of light around Jupiter. And those points of light are, of course, the large moons that Galileo discovered. And when Galileo discovered the moons of Jupiter, of course, it was heretical. It got him put under house arrest by the Spanish Inquisition. But he ignited a revolution. He put an end to the Aristotelian cosmology and really opened up the doorway to the Copernican revolution, the idea that the Earth orbits the sun is a star, and the stars that we see could be suns to distant planets. And in the decades after Galileo and the centuries after Galileo, we would come to learn that the laws of physics apply not just here on Earth, but also to these worlds and wonders beyond Earth. And with the advent of spectroscopy and other tools, we would come to appreciate that the principles of chemistry work beyond Earth. And then with the advent of the space age, we would explore the moon and Mars and Mercury, and we would learn that geology works. But when it comes to that fourth fundamental science, when it comes to the science of biology, when it comes to the phenomenon of life, the stuff of us, we have yet to make that leap. We don't yet know whether biology works beyond Earth, whether a separate independent origin of life exists beyond Earth. And part of what excites me about the time in which we live is that for the first time in the history of humanity, we can do this last great experiment. We can build the robotic spacecraft, design the instruments to get out there and see whether or not we live in a biological universe or one in which life on Earth represents some sort of biological singularity. So with that, I'll finish. I know I've run over time, but hopefully you've enjoyed this brief little robotic interlude, and I hope you're all doing well and you're safe and healthy out there. Thank you.
So Kevin, we have excruciatingly little time for questions. First, I do want you to know that people were oohing and ahhing out on the Q&A. So you got your oohs and ahs. One quick thing, just for an average person, what's something an average person can do to help encourage these missions to happen?
Yeah, that's a great question, and I'll sort of sidestep all the politics and all that stuff. But really, as taxpayers, you are the stakeholders in what NASA does. And honestly, the search for life beyond Earth is not that. There are many in the scientific community who do not prioritize the search for life beyond Earth, and that's a long. If you want, just read a bunch of Carl Sagan stuff about challenges and tribulations with that. But if you love this stuff, I would ask you just to express your excitement to your local politicians and anybody within NASA and any scientists that you know, because at the end of the day, NASA answers to the taxpayer, not just the scientists. And so please get engaged, get involved. We're doing the best we can.
5 to 10 years out, what are some of the big discoveries that you are, I'm not going to ask you to make a prediction, but what are some things that you think would be really exciting if they happened and realistic?
Yeah, the realism side of that is when it comes to the exploration of these alien oceans, not much is going to happen in that time frame. The Clipper spacecraft We'll hopefully arrive out of Jupiter within that time frame. I'm not the person to speak to any commitment in that capacity. A lot of that depends on the launch vehicle and when it hits the launch pad. But as you saw with the Dragonfly mission, that wouldn't even arrive to Titan until the 2035 timeframe. There's no commitment for a NASA lander. Even if we were given a start today, it would take about 15 years to land, and so we're talking mid 2030s or so. So within the next 5 to 10 years, I just hope that we can do a lot within our own ocean and really get a lot of the robotic technologies that I see being used for CubeSats and other spacecraft, use those in our own ocean and really advance our capability to explore the deepest, darkest, least explored regions of our ocean.
Tell us a little bit about the mindset. It seems like this is a common NASA, in particular JPL, mindset of really being excited about something that's going to take you like 20 or 30 years to make happen. Like, what is it that's, how do you get into that mindset, or do you feel like that's right? Am I right about that?
Oh, Rick. Yeah. A mindset. Is it a delusional mindset? No, we scientists, especially in this field, we're dreamers. This business is not for the faint of heart. I have been knocked down many times in my own career by many factors, many people, many things. And at the end of the day, it's a night under the clear, camping out under the clear night sky. That reinvigorates one about the time in which we live. Coming back to my final words on the big picture. I sympathize with Galileo. Galileo was under house arrest by the Spanish Inquisition. We find ourselves under a stay-at-home order from COVID. Humanity has been through many different things and had so many highs and lows. I guess at the end of the day, I'm just feel lucky to be alive and to be a part of this. And it's a generational effort. I sometimes like to say that these missions are the scientific cathedrals of our day. Planetary science and astrobiology is very generational, and we hand off from one generation to another as we try and get this great exploration done.
So we have multiple people asking questions about how you find a landing spot when you're trying to figure out, like, where do you park this thing? How do you figure that out?
Yeah, so the Clipper mission, at least in the case of Europa, one of the great things is that NASA committed to the Clipper mission. And so if we're fortunate enough to have a lander that follows on the Clipper mission, that data would be readily available to us and the science community to pick a scientifically interesting landing site. One could argue that there's, all of Europa is beautifully exciting, but we would target places that are salty and are representative of oceanic material. And then, of course, the engineers need to churn through that and give us the thumbs up on the kind of landing parameters that are consistent with the landing system. And in our landing concept, in our mission concept for the Europa lander, we employ a version of the sky crane that's used for landing on Mars. And us scientists, we have the easy job. We get to dream about the big picture of things. The engineers at places like JPL and Goddard and APL, et cetera, they're the ones that do the hard work and figure out how to make all this stuff possible.
So we're down to just like about a minute. I got a bunch of people asking about why Enceladus seems to be kind of lopsided. Why are there vents only on one side of it? Do you have any sense of that?
It's a great question, and one that my colleagues and I deliberate over. And Enceladus is such a curious little moon. We don't even really know how old Enceladus is. This is not work that I am directly involved with, but I'll just briefly highlight it. Saturn, the rings of Saturn are a canary in a coal mine for something bizarre having happened out at Saturn. dynamically, rings should not be stable for that long. And by long, I mean billions of years. And so the rings of Saturn could be telling us a story of a cataclysmic event, some Pluto-like object careening into Saturn, busting up a moon, creating the rings of Saturn, possibly even creating Enceladus itself tens of millions to 100 million years ago or so. So Enceladus could be quite young, and it could be like a fizzing tablet of Alka-Seltzer. Conversely, there are other models that show that, well, in some cases, the rings of Saturn could be billions of years old. So we just don't know, but that's part of the fun of all of that data that Cassini returned. There are dozens, perhaps hundreds of planetary scientists who are wonderfully tuning their models to figure out who's right and who's wrong in the history of Enceladus and the rings of Saturn and Saturn itself.
Well, unfortunately, that's all the time we have for questions today. Sorry, you had over 100 questions open in the Q&A. So
that's a lot of questions.
Very popular guy there. So, but thank you.
Well, thank you all for attending.
I'm Kevin, and thanks by the way,
Kevin.
All the advice and input with how the exchange operates. Our committee is critical.
Yeah, we really appreciate that, Kevin. And I think a couple of people commented about how amazing the images were. And I think that a lot of times we tell our presenters, you don't need to use slides, but when your slides look like that, we say, yeah, you use slides. So thank you for that. We also hope that you will be with us next week. I won't have my chickens by then, but what we will have for you is we're going to, I think we're calling it our STEM care package. We know that a lot of you are home with young children, and there's a lot of science that we might be able to offer that might be helpful to kind of maybe spend some time with those kids. And we're not saying that this is easy, because we know it isn't, and we're not saying it's homeschooling, because it isn't. Homeschooling is a whole different thing. As our experts have been telling us, this really is a form of emergency education. And so we've got Elizabeth Fogel, who is a longtime friend of the exchange. Liz is a PhD educator who's going to join us to kind of set some context for this. And then we have 3 Einstein Fellows, and Einstein Fellows are classroom teachers. Sometimes they're still in the classroom, sometimes not, but they are amazing teachers, and they're going to be here to talk to us about maybe just some perspective on how you can deal with this. And so we hope that this is useful. A little bit of science, a little bit of fun, and some amazing people to talk about this. So next week we will be back on our Wednesday schedule, and so we hope you're with us then. So thank you for being here today.
Yep. Thanks, everybody. Rough time to do a book tour, Kevin. I hope you do all right with this.
And don't forget to turn in for the next SpaceX attempt at the launch. It should be good.
Yeah, Saturday, right? Saturday.
Yep.
I'm gonna try it.
Weather holds. Exactly. Cool.
All right, thanks, everybody.
Thanks.